So let's talk about slopes and concavities of parametric equations. In other words, kind of connecting the derivatives of parametric equations. So let's say we're given a basic parametric equation where the where x is defined pretty traditionally by the cosine of t, and we'll define y traditionally as the sine of t. Now we know a parametric equation, so I'm just going to make a quick sketch over here. We know a parametric equation is just made up of a bunch of points, x's and y's. Now to get those points, x's and y's, we introduce this idea of time, right, so that we can figure out those coordinates. So for instance, at time equals 0, the coordinates of the point are 1, 0. If we pass a little more time, like pi over 2 units of time, we'd be at the point 0, 1, so on and so forth. So what I'm trying to indicate here, though, is like when we take a parametric equation, the parametric equation still makes a plot of x's and y's, right? So if we were looking to find the slope of the curve at that point, that slope, in other words, is just using points in the terms of x's and y's. So we do go back to our traditional definition of our slope as being the change in y with respect to x, because again, this curve over here is made up of a bunch of points x and y. Now the problem with that right now is x and y are in terms of t. So for me to try to say, like just as an example, how would y change in terms of x? Well, that's hard to answer right now because y is not given in terms of x. It's given in terms of t. Now we could just go ahead and eliminate the parameter and just rewrite these things without a t and represent them as each other, but that's kind of a little bit too much work that we want to do. What we want to see is we can actually use the chain rule here. So what I'm writing down here is by the chain rule. Now remember, the chain rule is just telling us a way to figure out a fraction in multiple steps. So if I was going to find the change in y over the change in x, well, I can't do that directly, but what I can see is if I set up this fraction, let's say I was able to find the change in y with respect to time, and then I multiplied that by the change in time with respect to x. Now this might seem like a weird way of writing that fraction right now, but if I wrote the fraction this way, those dt's would cancel, so I would be left with dy over dx. So I'm just going to erase those lines. So again, this will equal what I'm looking for. So again, this is the use of the chain rule. I can do this as a chain of events, find this first one and then the second one. Now the problem that we have up until this point is this dy dt, I can directly find that right now because y is written in terms of t. But the problem that we have is this one. Right now this is asking, well, how would t change if I change x, but that's backwards from this one. We don't have t in terms of x, we have x in terms of t. Meaning that's backwards to me. So I'm just going to rewrite this fraction one more time. So in other words, I'm going to start with dy over dt. But instead of multiplying by this fraction, I'm going to divide by its reciprocal. Now when I take the reciprocal, that's a lot better for me because that's dx dt. So what's the change in x in respects to t, which is now way better because I do have an equation that tells me explicitly how x is related to t. So that, which I'm just going to slide everything up and rewrite explicitly, I guess I'll just do it. I'm going to erase some of these lines. I'm just going to do it right here. So what we've summarized then is if I want to find the slope of a parametric equation, in other words, dy dx, I can find the change in y with respect to t, and then divide that by the change in x with respect to t. So let's just actually find the slope of this curve. Now we don't know at what point we want, but let's just find the general representation. So we just learned that in the last slide, if I was going to find the derivative, in other words, dy dx of a parametric curve, I could find the derivative of y with respect to t, and I can divide that by the derivative of x with respect to t. So that's fairly easy to do. The derivative of y, which I'll highlight now in red. So the derivative of y with respect to t, well, if I What's the derivative of sine of t? That's fairly easy. The derivative of sine is cosine. Now on the bottom, I would need to figure out the change in x with respect to t. And again, super easy to do because I have x in terms of t. So the derivative of cosine is negative sine of t. So the equation that represents the slope at any point on that curve would be given by cosine of t over negative sine of t. So let's look at the second derivative now. So that's what we've written. So how can we find the second derivative of a parametric curve? So we know that the first derivative, like that slope dy dx, was given by the change in y over the change in t divided by the change in x over the change in t. Now first and foremost, like as an example, like our other example was we found that dy dx, like in that first example, was given by something like the sine of t over the negative cosine of t. So this is our first derivative. How could we find the second derivative? Now, the biggest thing here, like this huge warning, is it's not just taking the derivative again. We cannot just find Now what I mean by that is using the same rule. We have this idea that when we have explicitly defined rules, like if I had something like y equals 3x squared minus 6x, and I asked you to find the first derivative, well, we just use the power rule and we get that. And if I ask you to find the second derivative, you just do that same rule again. You apply the power rule again, because we're trying to find the derivative of y in respect to x, and these equations are given in x. But the idea here is if we're trying to find the second derivative of this equation is not in terms of x. So we have to account for that, meaning there's got to be something else that we need to do. So again, super important, we can't just do the derivative again. Like we can't just recalculate dy over dx and then dy over dt. I can't just do it again. So like if this was my function, I can't just do dy over dt and then dx over dt. That would just be applying the rule twice. So we can't do that. There's a whole different way of finding this derivative. So then the question becomes like, well, how do we find it? So we're going to look back what we did at the first derivative for our pattern. We're just going to reapply the pattern and then come up with a general conclusion. So what we did, in other words, is like if we were given the ability, like we were trying to find dy over dx, what we realized was that if we're given like a parametric curve, is a lot of times those x's and y's are not given in terms, explicitly defined by each other, right? They're defined with this other variable t. So the idea is if they're defined by t, what we ended up doing was we were trying to find the change in y, which was defined by t, and divide that by the change in x, which was defined by t. So what we ended up doing was we just used t as what I'll call like an equalizer. Meaning, whatever we were trying to find the derivative on top, we were trying to find the change in y. Now, rather than finding the change in y with respect to the change in x on the bottom, what we did was we found the change in y with respect to t. Same thing on the bottom. We were trying to find the change, right, d for delta, change in x. So what we did with that one was whatever this thing was on the bottom, we called it an x. So to calculate, we did dx over dt. So what I mean by t as like the great equalizer is I took the derivative of the top thing in terms of t and then divided that by the derivative of the bottom thing in terms of t. Because again, that would allow us to use that chain rule. If I rewrote it, t becomes that equalizer per se, where it allows it to drop out and we're left with what we want. So we can use that mindset to find the second derivative. So I'm going to rewrite this second derivative. We're trying to find the derivative of what we found the first time. So in other words, we're trying to find the change with respect to x of what we got for the first time. Now the first derivative was dy over dx. Now we're just going to use the same exact idea that we used up here. We're trying to find the change in two quantities. Here it's y and x. Here the change is dy dx, and then this quantity x. So we're going to mimic what we did. So we can use t as our equalizer. So just like up here where I had y on top, and I ended up finding the derivative of y with respect to t, we do that same thing right here. So I'm trying to find the derivative of this thing, which I'm going to write in black again just to make it clear. I'm trying to find the derivative of dy dx. Now just like we did up here, whatever was on top, we found that derivative with respect to t. So whatever this is on top, I'm going to find that derivative with respect to t. Now on the bottom, what we did, whatever was on the bottom, we found that derivative with respect to t as well. So down here on the bottom is just an x again. So I'm going to do that same method. I'm going to find the derivative with respect to t of that thing on the bottom, which is just x. Now we can see by the chain rule is if I rewrite this as a multiplication, I would get the derivative with respect to time of that first thing, dx over dy, which I'm going to write better, dy over dx. And then that would be multiplied by the reciprocal of that fraction, dt over dx. So by this chain rule, again, we would see that those t's would cancel out, and we'd be left with, I'm going to write it below here, I'd have the change of dy over dx times 1 over dx. So then we do see on top, we see that change in y twice, so d squared of y, and on the bottom, we see that change in x twice. Now, why do I care? What I've just said was this will give me the second derivative. So on my new screen here, I just copied over what we were getting at the last screen. And this was the example we were working on before, like we found the first derivative. I'm just going to use that as a talking point. So like this is actually how we find the second derivative now. So like this is our formula. So what does this mean? So the top is differentiate now dy dx, that's our first derivative. So in other words, we're just going to differentiate the first derivative with respect to t, which is super easy. That's what we want it to be. Just find the derivative again. And again, if we look at our first example, our first derivative is in terms of t anyway, because again, we use t as that equalizer. So what we see on the top of our second derivative is just do the derivative again, recalculate the second derivative. However, what's different now is the bottom. That bottom is we have to divide again by dx dt. There's just an extra dx dt in our second derivative formula. So if you want to think of it as words, if you're going to find the second derivative, so let's do that here. If I was going to find the second derivative of that function, what I would need to do is the top part of our equation, what we realize by the chain rule, is we just take the derivative of our first derivative with respect to time. So here we could just use something like a quotient rule, let's say. So if I wanted to find the derivative of my first derivative with respect to time, I would do something like the low times the derivative of the top minus the top times the derivative of the bottom. I'm just kind of running out of speed here. And then that all divided by the bottom squared. And then what I would need to do is I would then divide it by the change in x with respect to the change in t. So I already know that x is the cosine of t, so dx dt, so cosine, the change of cosine is negative sine of t. And I'd obviously have to simplify that, but that's just a direct application of the usage. Let's just do a quick application or practice of that. So we're given a parametrically defined curve. So x is t cubed plus t, and the y coordinate is given by t squared. So we're asked, or we're tasked, I should say, to find the second derivative. So if we're going to find the second derivative, we need to start with the first derivative. So using our first derivative rule, we know that the change in y in respect to the change in x of a parametric curve will be given by the change in y with respect to time divided by the change in x with respect to time. So the change in y, so the derivative of t squared is 2t. The derivative of x with respect to time would be 3t squared plus 1. Now we need to remember our rule for the second derivative. If we're going to calculate the second derivative, so our second derivative of a parametric curve is given by the derivative with respects to time of the first derivative and then on the bottom we have an extra factor of the change in x with respect to the change in time. So what we're going to do then, I'm just going to rewrite some symbols. So we're going to differentiate with respect to time of this function, 2t divided by 3t squared plus 1. And then we're going to divide that by the change in x with respect to time. So the good part now is if I'm trying to find the derivative of this function, it is in terms of t. So we can go ahead and just use like a quotient rule here. So let's just go start applying that quotient rule on top. First, I'm going to do that top work, probably all just in green here. So to use the quotient rule here, we do low, so 3t squared plus 1 times the derivative of the top, and then minus the top times the derivative of the low, which is 6t, all over the bottom squared, so 3t squared plus 1. So that is the derivative with respects to time of our first derivative. And then on the bottom, I just have to calculate dx dt, which we actually already did, right? We did that in our first derivative. dx dt is just 3t squared plus 1. So simplifying, what we're going to see is we have, I'm just going to first distribute that 2. So let's just call this 6t squared plus 2 minus 12t squared. And then this is divided by 3t squared plus 1 squared. And instead of dividing by a fraction, I'm going to go ahead and multiply by the reciprocal. Which then I can see that this bottom is a little bit easier to represent, so I can just use an exponent. So what I get on top then, after I simplify, we get negative 6t squared plus 2. And on the bottom we have the quantity 3t squared plus 1 multiplied 3 times. Now once we have that second derivative, there's a quick application that's very common to go through. I could ask, like, what's the concavity at a certain point? So like, what's the concavity at t equals, let's just say, at time equals 1? So what we need to do there then is if we need to find the concavity, that's just a direct application of the second derivative. So I could plug that in really fast to here. So I'd get negative 6 times 1 squared plus 2 over so here on top we get negative 6 plus 2, which is negative 4, and on the bottom we're going to get 3, so 4 to the third, which is 64. So then this reduces to negative 1 over 16. I don't even really need to reduce it. What I can say is, because that second derivative, even if it's simplified or not, because that second derivative is less than 0, we know that the graph is concave and down when time is equal to 1.